special, I guess, external speaker for the Distinguished Lecture Series for this fall term. Good to see you all here. This is Professor John Howell. He's visiting us from Aberdeen. John is originally from Wales, spent some time in Liverpool and also in Bergen. He's also spent a lot in Utah. He probably is as familiar with these rocks as most other sedimentology stratigraphy professors who live here are, maybe more so. He has done a number of things through his career, including founding an actual oil and gas company called RockSource when he was in Bergen. He's been in Aberdeen since 2012, where he is a professor in petroleum geology. And he specializes in, what did you say here, application of analogs to subsurface reservoirs, so outcrop analogs for subsurface systems, and in novel data collection. And you'll hear quite a bit about his work in sort of virtual geoscience and visual outcrop models and related things in this talk this afternoon.
Great. Thanks, Carrie. Okay, so thank you very much for inviting me. Great turnout. I must admit I have serious building envy. This is significantly nicer than the building I have to work in. Anyway, so yeah, what I'm going to talk about today, and maybe I'm going to, depending on how quickly we get through the talk, I'll give you a little bit of a live demo, which is always a dangerous thing to do, but I'll give you a bit of a live demo towards the end of some of the things that we've been doing and where we see some of these applications going. So what I'm going to talk about is something we call the virtual geoscience revolution, and that might sound a little bit strong, but I'm going to start out with a fairly bold statement that we are seeing a colossal step change in the way that we do field geology. And it's been driven very much by this idea of virtual outcrops. And if you think that maybe sounds a little bit preposterous or maybe a little bit arrogant or something like that, then hopefully in the next sort of 45 minutes or so, I'm going to be able to convince you otherwise. So the basic idea would be that the last really, really major change in field geology and how we study outcrops came about with this. This is the publication, you probably recognize it, of William Smith's map in 1815. And Smith was basically the first person who had this kind of enlightened idea of putting geology, transposing geology onto a topographic map. And he did this amazing, I don't know if you know Smith's story, but he did this amazing thing of basically on his own, he mapped the whole of England and Wales. And he didn't even have a jeep or anything, he did it all on horseback. And this map here is remarkably similar to the sort of present day maps. So that was Smith. And that was, as I say, a phenomenal step change. And it's a really interesting story because ultimately he wasn't part of the establishment in the UK, and he was sort of excluded by his peers and the JOLSOC. Nobody would actually sort of recognize what he'd done until quite late in his life. He'd almost got to the end of his life before he was actually acknowledged for the pure genius of what he'd done. So basically, as I say, it wasn't until about 1831 that the Geological Society of London actually sort of recognized him and acknowledged what he's done. And if that sounds something vaguely interesting, if you haven't already heard of it or haven't seen it, there's a really good book. And it genuinely is. It's called The Map That Changed the World, and it genuinely did change the world from certainly in the way that we do geosciences. Now, what I would then go on to argue is that for 200 years, nothing really changed. Right, we still, when I was an undergraduate, you probably still teach your undergraduates in the same way that we still teach our undergraduates. You go out into the field with a paper map and a compass and a pencil, and you transcribe things onto the map, and then you color it in. And that's basically what we've been doing for 200 years. Nothing has significantly changed. And what I would say is that the revolution we're going through now is the first time in 200 years that field geologists have fundamentally changed the way that we're working. And if we're not talking in map view, back in the 1980s when I first started, when I started my PhD and we started sort of doing outcrop work and things like that, literally we used to go out and we would draw these big, what we called architectural element panels, but it was basically a scale drawing of a cliffside, whether it was fluvial channels in Spain or this is some Aeolian sands down in Namibia. It didn't really matter. The key thing is that we would actually have one person sat there drawing, the other person measuring, and we'd be sort of shouting or using walkie-talkies or whatever, and we'd try to capture the geometries and architecture of the cliff sections. And we took this to kind of a logical, or to an extreme, if you like, so that at one point I ended up down in Chile with a friend of mine, Adrian Hartley, who sort of invited me, not because he was interested in working in me geologically, just because actually I was the only climber he knew who was also a geologist who could make sedimentary logs. And he said, you need to come and look at this section with me, and it's a fill through a half graben, and this is a particularly cool section. It's about 70 meters of shallow marine sands, and then there is a cliff there, there is a fault scarp there, and that is actually the fault scarp, and this is a half graben that's filled up with shallow marine sediments, and you've got some kind of fan delta stuff interfingering with the shore faces over here. And I said to him before we went, he showed me some photos, I said, how high are those cliffs? And he said, oh, about 50 meters. So I went and bought a 60-meter high long climbing rope, and it turned out that the cliffs are all 70 meters, which is why all the logs finish 10 meters off the bottom. And I spent a lot of time dangling on a rope thinking, there has to be a better way of doing this. So when we spent some time in the early 2000s literally taking photo panels, and in this photo panel you won't be able to see it, but each place that there is a pseudo log, there is a person stood with a ball on a tape measure, and they GPS located that position, and then we would take one photo, then the person would move, and we'd take another photo and do that. So that you'd end up with some sort of scaled photo panels that enabled you to sort of measure things a bit more accurately and stuff like that. And we did that all over, well, that's the Panther Tongue. But we sort of collected lots of data like that. But basically, it was this idea, this is this half graben in Chile, it was this idea that basically standing there generally thinking, did I remember to put the handbrake on the car because the rope is tied to the car? And bits of stuff falling on my head thinking there has to be a better way of doing it. And I'd say around the 2000s, that's when I first kind of got involved with virtual outcrops, and I saw my first virtual outcrops. So when we say virtual outcrop, what are we talking about? We're talking about a photorealistic 3D model of a cliff where every pixel is geolocated. So this is just a typical example of a virtual outcrop. It's about 40 meters high and about 200 meters long, and they have a huge range of uses. Once you sort of get into it, you start to realize that this genuinely is changing everything about the way we collect data. So this is basically just a little example. When we first started out working with them, basically the first thing we did was did the same thing we used to do before, was we extracted the dimensions of geobodies. Whether it was shale lengths or channels or whatever it was, we actually went in and measured geobodies. We also used them for building reservoir models using the same software that people were using to model to model reservoirs in the subsurface. We would go in and digitize a bunch of points and measure and create surfaces, and then use that to sort of build up the 3D models. So those were the two main things. And everybody used to say, oh, God, what a waste of time. I don't really get it. I don't understand it. What's the point? And my view was always that there's two things about virtual outcrops compared to regular outcrops. The first thing is that there are data that you can collect in the virtual outcrop that you could collect in the field. You could go out here and hang off these cliffs and make dozens of logs, but it would take you a long time, and there's sort of health and safety issues and all that sort of thing, so there's things you can do that you could do in the field, but you can do them much faster. That's really cool. And then there is also data that you cannot collect yourself. You know, I challenge anybody to measure a surface that's dipping at 0.5 degree with a compass, reliably, given once the outcrop's all sort of weathered and things, to map out surfaces over really, really long distances in cliffs and things. So there's data you can get yourself, but it's quicker in the virtual outcrop, and there's data that you couldn't have got that are actually unique to this. So all this came about, a little bit of a history lesson. This is from my own personal perspective. Lots of people have parallel kind of paths through this. But basically, towards the end of the last century, the first real development was the idea of differential GPS. I tried using GPS previously, and it was rubbish. It put you like 200 meters away from where you were, and it was useless. But then along came differential GPS, and all of a sudden we thought we were super cool. We got all this kit, and we went down to South Africa, and we worked on a project. And basically, we worked on a project where people wandered around. Obviously, that's not South Africa down there, but people wandered around with a backpack on, tracing bedding surfaces, tracing surfaces, and making maps in that way. And that was the first time we actually tried to sort of make some digital terrain models ourselves and superimpose the geology onto it. Then I came across a guy called Carlos Aitken who was down in, or I think he still is, I'm not sure if he's retired, but down in UT in Dallas. And he was kind of way ahead of everybody else in this game, as far as I'm concerned. You know, and he was actually building photorealistic 3D models nearly 20 years ago. And the way he did it was he used a total station, just like they use for surveying the roads or whatever, and he built a robotic mount so that this thing would shoot the outcrop every 5 or 10 seconds, and it would move and shoot another point, and he'd build up a grid of points. And then he'd use an early form of photogrammetry to sort of create some models. And he was heavily funded by a Norwegian company called Norsk Hydro, which are now part of Equinor, but he was heavily funded by them back in the day, and that was just about coincident with the time I moved to Norway, so I got to work on some of the early models that they collected. And you can see that there's lots of sort of issues around with big holes in the model and everything, but actually these were really good quality virtual outcrops. And as I say, I'd say that he was about 15 years ahead of everybody else, or the Boca people. But for some reason, we still ended up hanging around on ropes a lot. And then everything changed. 2004, what I call the LiDAR revolution happened. And basically, suddenly, people like Jerry Bellion and stuff, they took terrestrial ground-based laser scanners out of the architectural domain, and they sort of took them into the field and started using them for geology. We got our first one in 2004, and we were super excited, because whereas Carlos's thing would shoot like a point every 5 seconds, this thing's shooting 10,000 points a second. And actually, all of a sudden, you were able to sort of collect vast swathes of data. And we were able to sort of build up. And the principle of LiDAR, if you're not familiar with it, is it's basically you have a static unit that sits still. It knows where it is because it's got a GPS on it. It shoots a laser beam at the cliff. Each time it hits the cliff, it records the position of that point from the time of flight, and it records that position, and then it's all sort of combined together. And you build what's called a point cloud, and then from the point cloud you also take a bunch of photographs, and you create a surface, and then you drape those photographs onto that. And this was great. One scan for it to rotate all the way around took about an hour. You do about 10 or 12 scans a day, and the whole lot weighed about 160, 170 pounds, so we used to think it was relatively portable. And it was great, and we were sort of collecting all these models and really feeling like, you know, we were doing something sort of exciting. And we built lots and lots of these 3D models. That's the point cloud, that's a decimated triangulated mesh, and then that's with the sort of photos over it. And we were actually able to generate some sort of things that really did look like the outcrop. There were some other advances along the way. We had quite a big group of people working on this when I was in Bergen. This is a classic example of a supervisor who has a plan in the pub, and then some poor student spends 4 years trying to make it work. And the idea was, you know, hey, we can map this outcrop. This is some dolomitized limestones in a quarry down in Spain, and you'll see why this is important in a moment. But, you know, from space, we can map lithology remotely if we use hyperspectral, multispectral imagery. So why can't we take that sensor and put it on a tripod at the same time? And then the reaction was, or from the remote sensing community, is, oh, well, the reason it works from space is because the surface you're mapping is flat and it's illuminated fairly evenly. As soon as you start looking at cliff sections and things, it won't work because you've got too much topography. And my reaction to that was, well, we've already mapped that topography with quite a degree of accuracy. So why can't we then use that to sort of model the solar illumination and everything, blah, blah, blah. So that sounds really easy after you've had a few beers. And so we got this poor student in, and he basically spent 4 years. This was the first hyperspectral scanner we had. If it looked homemade, it's because it was. And we sort of tested that. And now we had even more kit to take out into the field. So now we've got a LiDAR, and then we've got the scanner, and this doesn't run off batteries, it needs a generator, and blah, blah, blah. Anyway, even more junk to take out into the field. But ultimately, the results were pretty impressive, even if I say so myself. I was very excited. This is a classified image of that outcrop. And this is showing, I think there's a key to go with it. This is basically showing about 3 or 4 different types of limestone in various shades of blue, and then various different types of dolomite in the warmer colors. And we're actually able to see more in here than you can actually see in there, to differentiate different types of limestone. And also the best thing is you can quantify it. So you can actually press a button and it will tell you what sort of area or what percentage of the outcrop is made of what particular type of mineral. We also were interested in, I mean, I spent a lot of time in the Book Cliffs over the years, you know, and we were always struggling with the LiDAR because if we went out into the field, you know, we were limited by the range of the laser. So there's a bit of the cliff you get and scan. And then there's stuff that's out of the range of the lasers, just too far away to get a reasonable picture. And actually the laser's not so much the issue, but it's more the quality of photos you're getting and things when you're 1.5 or 2 kilometers away from the outcrop. And there's always big chunks, especially as you get further away, there's chunks that you can't see, holes in the model that we call the scan shadow. So again, another sort of stupid idea, why can't we put it in a helicopter and fly it along the cliffs? And then the feedback to that was, well, you know, that's not going to work because this needs to know where it is. And we were sort of tackling this problem, and then we met a bunch of Swiss and French people who were working in the Alps, and they'd had massive grants from the Swiss government to develop methods for mapping hillsides, because avalanches are a big thing in Switzerland, and also they're very rich in Switzerland, so they were happy to pay for all this. So anyway, they'd actually done all this. They'd actually taken exactly the same laser scanner that we were using. They'd combined it with the IMU, the inertial navigation system out of a cruise missile. They'd put 3 different GPS systems running in parallel on it and put it into the side of a helicopter and flowing it along the cliff. So we worked with them for a while, and basically the idea is now from the helicopter you're getting the optimal view at the cliff. So this is the kit. This is the Scan Ninja, hangs out the side of the helicopter, shooting with the LiDAR. There's a 50 megapixel Hasselblad camera there. And then basically this is that's all the kind of control unit. And to show you how quickly things have advanced, that is now pretty much equivalent to the acceleratometer in an iPad or in an iPhone or whatever other phones you use. All of that can be replaced with something that fits in a phone. But back in the day, this is like 11 years ago, this was kind of super exciting, super novel. And the really cool thing was that we could now collect really big outcrops. So whereas previously, you know, with an hour per scan or whatever, we were able to collect about, you know, maybe a mile of cliff in a long day, all of a sudden we put it in the helicopter, we flew it along, and we could collect like 20 or 30 kilometers in an hour. And all of a sudden we were able to make these really, really big models that were like half of the Book Cliffs or big chunks of cliffs in Greenland, or, you know, the whole of the half of the Karoo turbidites in South Africa. And the resolution of these models isn't quite as good, but for the sort of stuff we're doing and for the advantage of being able to see really big models, it's more than satisfactory. But the downside is helicopters are expensive, and we worked out, you can translate that to about $2,000 a mile or something similar to that in terms of how much it costs to collect this data by the time you've done everything else. And the biggest section we did was in East Greenland. We did a 55-kilometer section along a thing called Hurry Inlet, Jurassic, shallow marine, tidal sediments. Awesome data set, but yeah, pretty expensive sort of ways of collecting data. So the next thing was that I thought since they'd sold us a cruise missile guidance system, they might sell us a drone, but they didn't. They refused. But obviously drones suddenly came along. So in 2012, we spent a lot of money building and buying this piece of junk because initially our idea was actually this would at least be really cool of way of filling in the holes, the scan shadows in the LiDAR model, so we could take photographs and use them to fill in. And it was kind of coincident with the emergence of, or the re-emergence of photogrammetry and all this other sort of thing, that all of a sudden you could kind of get rid of the laser. And ever since 2012, I think the laser scanner has basically sat in the cupboard and not really come out. So we started working with drones in, as I say, 2012. That one was super expensive, but now they're really cheap. And the two things that have really sort of democratized this virtual geoscience revolution so that everybody can do it now, you don't need a $150,000 LiDAR scanner, is you can buy one of these for about $1,500. You can get Agisoft with an academic license for, I don't know how much, a few $100s. And basically everybody or anybody can build 3D models just flying the drone around and collecting that data. So the big question is always, where's the laser? And I guess, you know, probably most of you guys sort of know what structure from motion is or photogrammetry, but basically the idea is that you don't need a laser, because what it's doing is it's working off photogrammetry. So you fly it around, you take hundreds and hundreds of pictures that are all sort of overlapping. And the basic principle, which has been around as long as photography, is that a photograph is a 3D image compressed onto a plane. And that distortion as you take it onto the plane, basically if you have several different pictures of the same object, you get different sort of bends and twists in it, you can actually reconstruct that object. So that, as I say, that's an old idea. But what's new is that in around 2010, a whole bunch of new algorithms for doing this became publicly available. So previously, the photogrammetric, or the geomatics community had been obsessed with detail and getting everything super precise. And then this thing called structure from motion came along, and it basically said, we don't have to be like millimeter precise. We're trying to kind of reconstruct it. And it also does it in quite a clever way. It builds a rough model first of all, and then uses that to position the camera positions and sort of solves it then so you can build the fine model. And this software basically runs on a standard laptop or on a standard PC. You can create a reasonable model depending on how big it is in a few hours of processing time. So all of a sudden, you've got faster computers, you've got better software, and you've got a better way of acquiring image data from the drones. And all of a sudden, those three things combined, suddenly virtual outcrop geology sort of exploded. Suddenly everybody was doing it. I remember literally in about 2013 or 14 going to APG and pretty much being the only person, again, or one of a few select band of people talking about virtual outcrops, and then going back last year, didn't go this year, but going back last year, and I wandered around the posters one day, and out of 60 posters with outcrops on, 58 of them had virtual outcrops. And you suddenly realize, wow, this is taken off now. Now suddenly, because it's accessible to everybody, everybody's sort of doing it, and that's really good. So, yeah, skipped a slide. Sorry, that's not very good. I blanked some slides off, and I blanked the wrong one off. So that you can ask, how accurate and things and is it as good? The question we're always asked is, how does it compare to the LiDAR? So we've done lots of different benchmarking exercises to compare the 3D models you get from LiDAR compared to the 3D models you get from drones and so on. And then how repeatable are the models that you're getting from photogrammetry and drones? And the bottom line, well, we published a paper on it if you're really interested in it, but especially as a sedimentologist or for anybody who's interested in relatively large-scale structures, then the drone will give you a model that is fit for purpose. One of the things, this is a place called Argyle Ridge. This is basically looks a mess because it's two models that were collected completely independently. I took two separate flights. The photographs never came in contact with each other. Two separate flights, and then they were processed completely differently. And I loaded them both up into the software, and I noticed immediately. You notice immediately that is that. So actually, the space where it's put it like 100 meters out. So immediate thing is, oh no, what a disaster! It's all rubbish. No, you can't use it. But then I went in and I measured about 100 beds in here, and I measured the same 100 beds. And you find out that actually the accuracy, the consistency is incredibly high. So the models are very accurate, but just the position is sort of not precise. So you can sort of argue about whether that matters. If you're really, really worried about where it's placing the models, and there are sometimes good reasons to be wanted in exactly the right real-world coordinates, then you can put out a bunch of ground control points and you can process the model with the ground control points in, and it will be super accurate. But if you just want to measure that channel and the thickness of the beds and how the thickness of the beds is changing and all that sort of stuff, it doesn't necessarily really matter exactly where it is in 3D space anyway. So a big thing about when you build these models is to decide what is the purpose you're going to use it for. What do I want to get out of this model? Because there is always going to be a point when you fly in and it'll get blurry. And another thing that's kind of annoying is you show people models and the first thing is they look at it, oh, that's quite cool. And then they fly straight in and go, oh, it's not very good. It's just like, yeah, but you're like that far away from the rock, and of course it's blurred. It's a camera on a drone that's 50 meters away. So, but if you didn't want that to be clear, then, you know, obviously you'd fly it much, much closer and everything like that. But you've got to decide, what do you want the model for, and what are you going to use it for, and what do you want to get out of it? And it basically, this kind of accuracy precision thing, basically that's this little matrix I'm sure everybody's familiar with. Precise and accurate means you're shooting there. Precise but inaccurate is what we're talking about here. So it's precise, so all the measurements are right, but it's inaccurate. And then basically, you know, it could be that is precise but not very accurate. This is where we are with these models without ground control points. And as I say, I think as long as you're aware of that, it's not necessarily a problem. So it depends on the purpose. It depends on what you want to do with the model. Sometimes it's important, sometimes it doesn't really matter. And it might be important if you're working on really large sections and you want to string together multiple outcrops and things like that. But there are also other ways around that. So where are we? Actually it's 2019 now, sorry, I should have updated that. Anyway, where are we? We've got cheap, high quality drones or UAVs. We can acquire data rapidly. We have software that allows us to process those data on a standard laptop pretty quickly. And all of that leads to this idea that virtual outcrop geology, whatever you want to call them, digital outcrop models, they've got lots of different names, but this idea that virtual outcrops are no longer a specialist kind of pastime or methodology, they're actually available to everyone. So this is what we say when we mean that they are democratized. And people, you can collect them for, the number of uses is almost infinite. So whatever you can do in the field, or nearly everything you can do in the field, you can do here, and you can do a whole load of extra things. So the sorts of things we're doing with them, we do reservoir analog studies. This is another little outcrop in the Book Cliffs on just by the old Castlegate mine. But basically, you know, we do an interpretation, we overlay it on the outcrop. You can build a geomodel of it. You can extract semi-variograms for the statistics of the bodies. You can extract object dimensions for the shapes of the bodies. You can extract Fashi's proportions curves and things like that. And this is all the stuff that people who are our sponsors, who are kind of working in the subsurface, this is all the kind of information they need to build their 3D reservoir models of the volume, where they've just got one borehole or a couple of wells that are a mile apart. This is what they want. They need these geostatistics to sort of populate and build realistic models. So that's our day-to-day job. But then we also kind of, the oil price crash here helped. But we've also been doing other sort of stuff, which I think is pretty cool, sort of looking at volcanoes. One volcano in particular, this is Stromboli. And this is a small volcano just down on the southern tip of Italy. And literally, if you ask a child to draw a volcano, they would draw Stromboli. It's a cone that comes out the sea. It's about 3,500 feet high. That's actually a town, those white dots there. And the main active lava field for the volcano is here. That's the sort of present day active crater. If you know anything about volcanology, you will have heard about Strombolian eruptions. This is the type section. And basically what happens is generally the volcano just goes off about every 20 minutes and produces little eruptions that are great for tourists and really cute. But from time to time it does really big eruptions, and it's obviously kind of nice to sort of predict, or it would be good to be able to predict those. The whole thing is covered in a massive network of sensing tools, tiltometers, seismometers, gas detectors, all this stuff, cameras, thermal cameras and everything are sort of splattered all over it. So we thought if we were going to sort of try to play around with volcanoes and monitoring volcanoes with drones, this is a really good field area or a real good test case, because you've got the sort of original data. So we went down there. Basically, we sort of had some ideas to go down there, and the first one was just to map the volcano using the standard drone technology, the virtual outcrop technology. And then the next one was to sort of see if we could superimpose thermal imagery onto this. So you can take, you could put a thermal camera onto a drone and actually sort of see if you could see the thermal structure of the lava field. And the first time we went out there, again, we had to build the thermal drone, and it was kind of mixed success. The second time we went out there, we managed to sort of build a thermal model, which is shown here, draped on top of the sort of the standard textures model. And then I'm not sure if you're aware, but July the 3rd this year, there was a massive eruption here, and actually unfortunately killed somebody, but there was a massive eruption here, and there is currently an active lava flow. So we went scurrying back there to see if we could sort of collect some extra data, especially with the idea that actually we had probably the most detailed terrain map of the lava field in existence before the eruption, so obviously it makes sense to go and sort of have a look the second time. So basically that's just a little bit of video clippage. Basically this is just showing us that's us sort of flying the drone. That's a standard Strombolian eruption. This is our little team here desperately featuring lots of DJI drones in the hope that they'll give us some, which they do now actually. But that's the drone with a thermal camera on it, and just sort of flying it around. And actually, when you come home and say, "Yep, I stood on the edge of an erupting volcano flying a drone about it," that's actually pretty cool. That's a good day at work, that is. Oops. And basically, just a little bit more footage, sort of just showing the drone. That's the kind of pictures of eruptions you get from the drone, which is quite cool. And then you can even get thermal eruptions. So that's actually obviously an eruption from the thermal drone, and you can see all the bits of sort of lava and slow it all down and everything to make it sort of cool. So that's kind of a little project we've been doing on the side, and there is actually a. If you search Aberdeen University Stromboli, there's a little 20-minute video that those sections were cut out of that sort of tells the story of that, which is the kind of stuff the university really likes. But then, as I say, July the 3rd this year, there was a huge eruption, and basically so we went back there, and this is actually now thermal imaging and this is a thermal 3D model of the new lava flow. So previously we were mainly working over here. The eruption was over here. You can see a massive chunk of the edge of the crater has disappeared, and you can actually thermally map out the structure of the lava flow, which is great for some volcanologists in our department who are trying to build numerical models of how lava flows move, and they didn't have very good temperature data. Because all this is radiometric. Every one of those pixels, you can go in there and see what the actual temperature is. And just to put that into a... Oh. And that is the sort of thermal 3D model. As I say, you can see it's actually got a sort of distributive pattern coming out of there. You can see which areas are active. There's actually some little lava tubes at the top where it sort of disappears into the lava tubes. And yeah, and you can take sort of cross sections to look at you can see what the dip and everything is, obviously, because you've got the terrain data, but you can also take thermal profiles and things like that across it. Other stuff that's kind of interesting, got kind of, again, loosely interested. After I heard about how they'd rebuilt or they were reconstructing Palmyra, the Roman town in Syria, after ISIS came and tried to blow it all up and knock it all down. And I heard that they were crowdsourcing photographs from tourists who'd been there over the years to see if they could build photogrammetric models. You know, if you have enough tourists taking photographs, you eventually will have enough of a 3D model. So I thought, I wonder if we can do that in geology. So this is a road cut, which you may have visited, down right opposite the Arches Visitor Centre with some really cool faults in it. And about 15 years ago, they widened the road. The edge of the road used to be here, so they widened the road. So a little bit of crowdsourcing. It wasn't as successful as I'd hoped it'd be, because it dates just before that everybody had a digital camera, so there wasn't so many photographs around. But off the Tectonics kind of bulletin board thing, I was able to sort of crowdsource enough photographs to sort of build a 3D model of the outcrop before the road was widened, and you can sort of superimpose the two together, and what you see then is you realize that you can sort of start to map out the geometries of the faults and things. And there is potential for sort of building 3D models and things and capturing outcrops that don't exist anymore. So that's kind of cool. People, obviously the Mars people, are doing a lot of this 3D modeling. They're driving a rover around with a camera on it. You can now go online and go on 3D field trips and sort of wander around Mars. So there's, you know, as I say, the boundaries are almost limitless. And then looking into the future, one of the big initiatives I'm sort of working on at the moment is that this is the database that we give to our sponsors, which is why they give us lots of money, which allows us to buy lots of toys and go to nice places. But we have a database of about 400 virtual outcrops. And we built this purpose-built web viewer, which will allow you to kind of, you don't need to install any software or anything. You can actually just fly around the models, and it's all sort of handles really big models and layers and all this sort of stuff. So what we're going to do is we've finally managed to persuade the sponsors to sort of allow us to make that viewer and stuff publicly available, and most of the outcrops we've collected publicly available. And what we want is that's going to happen in about November this year. And then what will happen is that people will publish their outcrops. Once you've done your work with it, once you're finished with it, if you want to share it with a wider community, is you'll be able to go here and you'll be able to upload your model with a bunch of metadata, which makes it searchable, which means anybody can find it. And you'll be able to sort of upload your data and share it with the wider community. And you'll be able to control whether, other people can download it or whether they can just view it, and whether it can be used for commercial purpose, or all that sort of stuff. You'll be able to control what happens with your model. But ultimately, it's actually like 3D publishing. You'll be able to sort of put your models out there, and so we don't have to keep going back and collecting the same data again and again. Virtual field trips and virtual reality. I'm going to show you a virtual field trip for the last sort of 10-15 minutes of this, so I won't talk too much about virtual field trips, but we're also working with virtual reality, so you stick your headset on and you are completely immersed within the outcrop, and it is genuinely as cool as it sounds. You put it on and suddenly you're in the outcrop, and you can fly around the outcrop, and you can go to different places and different things pop up in front of you and all that sort of stuff. So we're working with a couple of companies that's actually developing virtual field trips, both just on the screens but also sort of immersively. We've also got a bunch of algorithms now. So this is a big outcrop from up in Svalbard, but basically we can now generate sort of synthetic seismic from the outcrop. You put in a bunch of properties, and then you put in the sort of wavelet that you want and everything, and then it'll basically create a synthetic seismic and drape it over the outcrop. That's a really good one for scaring oil company people, because you show them this outcrop with all this kind of detail in, and they go, oh, that's really cool. And then you go, yeah, but that's what you see on your seismic. Or they go, oh, we don't have any of that in our data. It's all completely layer cake. Oh, really? Watch this. So it's really kind of a very sort of cool teaching tool, and a good sort of tool for sort of sharing that sort of thing. I think, so that's kind of already sort of coming, but I think it'll become much more mainstream. I think augmented reality in the field, the fact that you can sort of go to the field, and instead of now sort of saying, stick your Google glasses on, or whatever it's not Google glasses or whatever it ends up being. And basically, instead of saying, the layer by the balance rock next to the tree, by the boulder, no, the big round boulder that looks like an elephant, yeah, up from there, just up from there, go along. And instead of all of that, suddenly everybody's wearing glasses, and the instructor clicks a button, and you get an overlay with the stratigraphy on it. You could even overlay well logs. You might even overlay seismic data directly onto the outcrop, or a geomodel that you've built. You can overlay all of these things directly onto the outcrop whilst you're out in the outcrop. So this kind of technology, again, the technology exists. It's all being done. It's just sort of available. We need to sort of adapt it within the geosciences. And then there's augmented reality in the classroom. So the HoloLens is not really there yet. It's this kind of Microsoft thing that this guy's wearing here. It's not really there in terms of its graphics processing power to handle outcrops, but it's not very far away from you being able to say, right, okay, draw a box there, stick the outcrop down, and everybody stood around it, and you spin it around, and you point to different things, and you sort of fly around it and things like that. Again, all that technology is pretty close to being there. It just needs slightly better graphics power in that, but that's why I'd say that's only about a year or 2 years away. Then there's kind of, everybody's into data, machine learning, artificial intelligence, blah, blah, blah. So we've got a project that's just starting now, where we take the virtual outcrop, this is a manual interpretation, and this is a first pass machine interpretation that's been trained off a small subset of that outcrop. So the idea is that you can suddenly automatically, or a machine will learn from the interpretations you've done previously to interpret the outcrop. And you can suddenly generate or at least a first pass of the interpretation. For us at the moment, the biggest bottleneck we have is students sitting there getting repetitive strain injury, sort of mapping out every sand body. If we could automate that process, which is absolutely doable, Again, Google trains algorithms to separate dogs from wolves and all this kind of thing. So it's completely doable. It's just a question of applying it in our sphere. So our first kind of pass, obviously, we were able to get a sort of 85% match, and I think we're going to improve on that significantly as this project goes on. So why are we using virtual outcrops? Well, you bring the outcrop home to the workstation, which is great. It lets you access huge areas of the cliff that you couldn't otherwise get to. You just stand there and kind of point up at it, or you get a rope and abseil down it. But you can collect huge volumes of data now very, very quickly, much, much faster than you can by sort of doing it in the traditional ways in the field. There are methods I've shown you with the hyperspectral imagery to actually map and quantify the mineralogy and the composition of those cliffs directly in the field. And you can go on field trips, and I'm going to show you a little virtual field trip in a moment, but without actually having to leave your desk. And I think that is really, really valuable. That is the future. I mean, everybody hates me for this. When I go into oil companies, they go, "You're going to stop me going in the field, aren't you?" I said, "Probably." But it doesn't necessarily completely remove the field. It can augment it. So we already, with our undergraduate and our master's kind of field trips, we'll take them on a virtual field trip, show them what they're going to see, and then make all the data available for them to have a look at when they come back. That actually makes the field trip more valuable. But also, you can put together a field trip. If you want to look at deep water deposits, at the moment, the current sort of way of putting together a field trip is very linear by geography. So, you go on a field trip to the Buck Cliffs and you go, from one set of locations to the next. But imagine if you could put together a deep water field trip, for example, could be anything, where, you look at the slope channels in Spain, you look at the basin floor fans in South Africa, you look at the collapse complexes in Mexico, and you can literally go to outcrops all over the world in a space of a few minutes. And the other thing is that, for the majority of people who are sponsoring our work, and it applies to most of us, if I want to work out what a flood tidal delta, or I want to see a flood tidal delta in outcrop, I sign up for a field trip that's going next May, and by the time I get on that field trip, I've forgotten why I wanted to come on it. But here you can just immediately, literally just kind of go find the appropriate virtual outcrop, fly there, and you're there instantly. And you can maybe answer the question. It might even just be that, yes, I definitely need to go see this in the field, but at least you've sort of you've cut out a lot of that wasted time. And there is also geoheritage, and there's also sort of field trips to locations that are either logistically very difficult. A lot of the stuff we do up in Svalbard and Greenland, it's super expensive. Most people will never get to go there just because of the cost and the hassle of getting there. Other parts of the world, you can't go there any longer, or you can't go there for sort of geopolitical reasons. So you can bring all of those into the aspect. And then finally, not last but not least, we have students who have mobility issues. They can't sort of run up a cliffside. But this enables anybody, literally anybody who can sort of look at a screen or whatever, can actually interact with the geology, and they can have an experience that is akin to going to the field. And obviously the reason the oil companies love it, apart from the health and safety stuff, is the significant cost savings. So that's the kind of, and as I say already, it supplements the existing field trips. So basically that's my thesis, is that over 200 years of geological mapping, nothing really changed. And then all of a sudden, about 10 years ago or 15 years ago, around the start of the 21st century, basically we have this revolution. And it's a revolution that's going on now. And I would say we're only in the beginning of it. It's really hard to sort of think all of the places these advances in technology will take us. But I maybe would say maybe it's not quite as big a step as William Smith putting his boundaries onto a map for the first time, but I would say I think it's comparable. And I think it has the potential to revolutionize how we sort of think about geology. And I would say, for the first 10 or 15 years of that, it was very much about specialists with very expensive LiDAR kits and all this sort of things, and there wasn't software and all that sort of stuff. I would say now it's completely democratized. Anybody who's going to the field pretty much can do this. And as I say, a drone you can buy or borrow, a relatively cheap drone. The software is relatively cheap. The software to do the interpretations you get for free because we give it away. So all of these kind of things, it literally is available for everybody to do. And I think, you know, it's revolutionizing how we sort of collect and use field data. And there's massive potential for the future. So yeah, that's our sponsors, that's our team. But what I'm going to do is, before we finish, is I'm just going to use the last 15 minutes or so just to take you on a virtual field trip to the Book Cliffs. So where are we? Let's start with this one. So basically, this is the kind of virtual field trips that we put together. So this is all actually in a 3D viewer. And I'll just show. So this is where we're going. We're going to the Book Cliffs in the southern part of the Book Cliffs, down in between Woodside Canyon up here and the town of Green River is over here. We can sort of show how the world looked back in the Cretaceous. And we can say that, you know, we're going to home in on this bit over here, just sort of overlaying Ron Blakey's maps in the whole thing. There's our geology map, and we can sort of bring on the satellite imagery just to show the outcrop. And then we can turn on the virtual outcrop. So this will just take a second or two to load, because it's quite a big model. So this is one of those big heli LiDAR data sets that actually runs from here at the entrance to Woodside all the way around to, they say never do live software demos. There it is. So the satellite image is just a 2D plane. You can with these, you can take in a regional terrain model. We've done that, and superimpose on a regional terrain model, just overlay some kind of Google Earth imagery or satellite imagery. We're just using that satellite image to sort of orientate ourselves. But you can see as I fly in, now you can see the 3D model of the cliffs. And you start to see, you know, we've actually got pretty good resolution in here. You can see the individual shore faces. You can see the non-marine deposits. That's the Castlegate sandstone. You can see the bar forms and things in the Castlegate. And that's a section, as I say, that's about 35 kilometers long. And I can sort of fly into this and zoom in, and I can sort of superimpose some interpretation lines. I can superimpose a log on that. I can sort of fly in and pull up, I can incorporate logs into the panels, and as I say, I can sort of then drape those onto the outcrop to show. So again, this is a sort of great teaching tool. And then we can sort of tie it in with other data. So that's our big regional cross section through the Book Cliffs. That's a 120 kilometer long section. The green is the coastal plain, the yellows and browns are the shore faces, and the gray is the Mancos Shale. And we've sort of, you know, turned that into a chronostrat diagram if you want to explain to students about chronostrat. We've also sort of created synthetic seismic of that. So if you want to see what that panel would look like on a 25 hertz seismic, that's what you'd be seeing. And then we've also created, so these are just correlation panels again from log sections around about the ways in here, and we can sort of use that to sort of get a better understanding of the different rock units. We can pull in modern analog data, which is coming. So that's a modern analog now. This is the Paraiba del Sul Delta from Brazil, but it's in at the same scale, and it's sort of showing, you know, that's the outcrop compared to what a depositional system. You can see all the nice beach ridges, and you can see the distributary channel, the trunk channel coming in here. That's sort of showing, that's kind of bringing that link between the modern and the outcrop back in again. You could superimpose an oil field onto that. So this is just a typical Brent field. You can see the sort of scale of the oil field with respect to the analog, both the ancient and the modern analog. And finally, for this, we can sort of build. Again, it's going to take a little bit of time. So a Petrel model has been built of this strata based on those panels and logs and the virtual outcrop. Obviously, this is virtually expanded because you can see the virtual outcrops just down in there. So I've sort of vertically expanded this to make everything sort of so you can see everything. But you can actually see now the whole thing sort of captured in 3 dimensions. And you can sort of fly around this and you know, see, and you can go, there's an incised valley there which you can sort of go in, or a channel complex which you can sort of go in there and see. And then if we want to zoom in to, this is a canyon. You saw a virtual outcrop of this, but this is now sort of stepping down a scale. So this is a single canyon, This is Thompson Canyon. There's a car park there for scale. This model is only about 2 kilometers long, but it's a little bit higher resolution. I can sort of fly into the end of that, and I can sort of pull up a log. I can see the facies. I can see the deposits. I can sort of compare the log to the deposits. There's some nice wells been drilled in this section, or 2 wells been drilled by Shell and Exxon. They drilled 2 research wells here, so we can sort of compare the outcrop back to how it looks in the subsurface. Again, I'm a big fan of modern analogs. So this is that estuary superimposed. This is a tidal estuarine complex superimposed on a modern day estuary, and again with sort of matching up some of the facies at the same sort of scale, you sort of get an idea of how that outcrop fits into the depositional system. And obviously we can add that, we can add to that a sort of interpretation of the tidal flats and the subtidal channels and things running through the middle of the outcrop there. We can map out surfaces in the virtual outcrop. That's the base of the estuarine unit, that's the flooding surface across the top of it, and I can create planes. And then I can, again, create a nice little Petrel model that shows that's the yellow and the green is the sort of tidal estuarine package. The orange and the red is the shore face. So I can see exactly how this would look in a model, and I can even overlay that model directly onto the outcrop if I want, and sort of compare grid resolution issues, compare what we can see in the outcrop with what we actually see, in the 3D model. And then if we want to take it down a step again, this is actually a 3D model. This is actually a 3D model of a hand specimen of the sandstone. So you could actually place this within the model and say, right, if you want students and things to see what it's like, what the sandstone actually looks like, you can actually, it's not quite the same as handling it, obviously, but you can see, and you can do this with fossils or any other sort of feature. And then just to take it down the whole way, this is actually an SEM stub from that hand specimen, and we've got this fancy new SEM which you can take photographs of different angles. So I thought, well, that's just like using the drone. So we flew the SEM around for a couple of hours, or sort of a few minutes actually, and that's a 3D model then of that sandstone. And you can sort of, you can't fly through the pore spaces, but you can fly right up to the pore spaces, and you can see the quartz overgrowths, and you can see the kind of clay minerals and things like that. So the point of that very quick run through, I mean, normally that virtual field trip I would spend a little bit longer on it, but I'm aware of time. But basically what we've done is we've gone from a regional seismic scale. We've seen virtual outcrops that are 35 kilometers long with big synthetic seismic sections that are 120 kilometers long all the way down to the pore. And every step of the way we can use this sort of virtual outcrop technology and these virtual outcrop techniques as sort of teaching aids, as research aids, to sort of help people sort of to communicate the geosciences, and also just to help people sort of understand, and also to collect data that's interesting. So I think I'll leave it there. Thank you very much.